Had circles in the last video. Let's talk about ellipses. So verify the elliptical equation x over a squared plus y over b squared is equal to 1 is parameterized by c of t is a cosine t, b sine of t. We want some bounds on this as before. The interval of length 2 pi is going to work here. So how are we going to do this? Let's just plug in x is a cosine t, y is b sine of t in here. And what do we get? A cosine t over a squared plus b sine t over b squared. Of course, the a's will cancel, the b's will cancel, and we're just left with cosine squared t plus sine squared t, and that's equal to 1. So that checks. If we want to plot this, let's say that a is equal to 4 and b is equal to 2. And so to plot this, let's do some sample values at when t is equal to 0. Well, let's rewrite this. It's going to be c of t is 4 cosine t and 2 sine t. When t is equal to 0, we have 4 comma 0. So that's over here. When t is equal to pi over 2, we have 0 comma 2. When t is pi, we get minus 4 comma 0. And when t is 3 pi over 2, we get 0 minus 2. So there is our ellipse that we can trace out here. Okay, another thing to talk about has to do with different, we already mentioned this in the lines video, but the same curve can have different paths that we take. Different ways of traversing it. So let's describe the motion of the particle along these three curves, and we're going to assume that the allowable t values are as big as we can have. So c1 of t is t cubed comma t to the 6th. c2 of t is t squared comma t to the 4th. c3 of t is cosine t cosine squared t. Now, if there's something you should realize here, is that in every single one of these all satisfy y is equal to x squared, right? T cubed squared is t to the 6th. T squared squared is t to the 4th. Cosine of t squared is what? Cosine t squared, cosine squared of t. So all of these are going to trace out part of the parabola y is equal to x squared, but we're going to see that all of them do it in a little bit different way. So for the first one, c1 of t, as t runs from minus infinity to plus infinity, t cubed also runs from minus infinity to plus infinity. So what this says is that we can achieve all allowable values of x here. All allowable values of x here happen. And so we are moving from left to right, go through the origin. This one is c1 of t. Now what about c2 of t here? Well, realize here, x is equal to t squared. That's never negative. That's always non-negative here. So we're only going to trace out, the only thing we're going to do here is we're going to trace out the right half of the parabola. But think about what's going on. As t starts out very negative, like from minus infinity, t squared is actually very positive. So we actually trace things out twice. So as t is negative and is increasing, x is decreasing, we come along here once, we hit 0, and then t is still increasing, and then we go back out. So when t is very negative, like this is t is minus 10, minus 9, minus 8, minus 7, minus 6, minus 5, minus 4, minus 3, minus 2, minus 1, 0, 1, 2, 3, 4, 5, we go in and then we go back out because x can never be negative because we're squaring t here. Okay, the third case to take a look at here, cosine t, cosine squared t. Now, the thing that we realize is that x can never be outside of minus 1 to 1. X is never outside minus 1 to 1. And so what happens is that as t, just runs along, we just continuously oscillate back and forth here. When cosine t is 1, we're over here. When cosine t is minus 1, we're over here. We just keep going back and forth. We repeat this infinitely many times. So yeah, all of this is to say that just because you have different looking parametrizations, they all might trace out the same, parts of the same curve. But just because they're tracing out parts of the same curve, like they could trace out different paths, different parts, they can have very different behaviors. That's the moral of the story of this example.